Boa tarde a todos. A gente vai começar agora uma apresentação. O tema dessa palestra de hoje vai ser How Vector Database are Revolutionizing Unstructured Data Search in AI Applications. E nós temos o prazer de apresentar, de ter Frank Liu como apresentador. Ele é Head of AI and ML at Zilliz, with more than 10 years of industry experience in machine learning in hardware engineering. And we hope, esperamos que todos gostem da apresentação, and we'll thank Frank for the time and for the presentation to us. Frank, it's up to you. Thank you very much.
Thank you for that wonderful introduction. And thank you for inviting me here and having me give this presentation as well. Today, I want to talk about, I'll talk about vector databases, I'll talk about unstructured data, but I think more broadly, I want to talk about the generative AI space as well. And there's a lot of companies out there, there's a lot of different projects, a lot of different people doing a variety of great different things. And I really want to focus on what are the really unique aspects, what are the opportunities for unstructured data, what are the opportunities for vector search, and what are some of the things that you might want to watch out for as well. I put in slideshare mode as well.
This meeting is being recorded.
Databases and unstructured data search a little bit more broadly. But first, I'll introduce myself very quickly. I'm Frank. I'm head of AI and ML here at Zilliz. There's my email down there. It's just frank@zilliz.com if you want to connect with me at any moment in time. And then a bit about us as well. So we here at Zilliz are the company behind Milvus, and Milvus is, by many metrics, the world's most popular open source vector database. For folks who really aren't that aware of vector databases just yet, we'll get there in a little bit, and hopefully it'll be a good. You'll understand how vector databases and unstructured data tie in together very well. At this point we have something like 27,000 stars on GitHub and over 10 million Docker pulls as well. So a really, really vibrant community that's built around this open source project, and many ways to deploy it as well, from Milvus Lite to standalone to cluster. And we can get to that a little bit later in the presentation as well. But moving forward, I want to talk first about the generative AI landscape more broadly. There's a lot of excitement around this area, not just because of ChatGPT and other large language models, but because we have all these diffusion models as well. We have ways of, let's say, generating images and generating videos simply based on a prompt, right? Using natural language. So there's a lot of excitement around this area, and by that extension, there's a lot of companies as well. There are an absolute ton that are in this space. Some are in infrastructure, some are building these models themselves, many are at the application level, doing horizontal or vertical applications. You have open source infrastructure, many APIs, and quite honestly, more consulting companies that I would have imagined as well. Many of the companies on this list are actually from Brazil as well. So there's a really, really variety, not just in Silicon Valley here, but also in South America, too. But it can be really, really hard, to piece all these companies together and to understand what everybody is doing in this space. So what we like to do is we like to distill things down into three main pillars. And these pillars, two of these pillars, I think it's pretty clear what these pillars are, right? And what they do. So you have these models, you have these model providers. Folks like Meta, like Google, like Anthropic, OpenAI, Mistral, Inflection AI, Cohere. All these folks are providing large language models or embedding models or some other type of model. So Hugging Face has many models that do more traditional tasks as well. For example, some type of models that allow you to get some sort of intelligence out of your data, right? Allow you to transform your data into a way that into something that you can actually have actionable insights over. Same goes for LLMs too, right? If we look at the lower left-hand box there, then we have computation. And computation, you can really think of it as a way or framework to be able to run your models. So I have all these models that can give me all these great insights that I can use to do analytics and so on and so forth. And I need a platform to be able to run them on. Right. So NVIDIA is obviously one of the big ones out there. They provide GPUs, but then we have these actual sort of like tensor processing units or specifically designed for neural network inference, such as Sambanova or GraphCore, ROC. And you also have a lot of CPU providers that are sort of entering the space as well. So, for example, we have done a lot of work with Intel, and we work with AMD and with ARM as well to actually make to make use of their computational resources. But the last pillar that I think is really, really missing, and I'm not gonna say really missing, but I think the last pillar that a lot of folks generally tend to leave out is the data side of things. Is the data pillar. You have a wealth of data out there that you can run these models on, you can train models on this data as well, and you want to be able to extract actionable insights out of these different pieces of data too. And that's really where a vector database fits in, right? You have these models that you can run. You have the computation that you can train and you can do inference on these models on, and then you need the data piece too, right? So you need data to be able to perform inference or to be able to perform training across these models, so that you can do it, so that really you can make something out of them, right? And that again is where a vector database fits in. And what a vector database is good for is really storing, indexing, and searching across massive quantities of unstructured data. But I think going beyond that as well, there's a lot more things around unstructured data that it makes sense that you want to be able to get up and running too. So for example, you want to be able to do ETL. So you want to do unstructured data ETL across that data. A lot of that ties in very closely with the idea of models and computation, right? You need computation and you need models to perform unstructured data ETL. Similar thing for data pipelines as well. And then you want some more of those traditional stuff around that too. So observability, security, and encryption. And as we move forward, all of these things are going to be very, very important, not just for the Gen AI space, but for a lot of industries and for a lot of companies, for a lot of organizations more broadly as well. And that is a key important thing. And I hope, if there's just a single takeaway from this presentation, from this talk, it's that unstructured data is going to be really, really important. It's important for us moving forward. It sits at the intersection of databases, data infrastructure, and AI and ML. And we're going to have these really, really vibrant communities built around it, just as we have vibrant communities built around the models and around the computation side of things as well. So again, that was a quick introduction to Milvis, to Zilliz, and hopefully a good high-level overview from 10,000 feet, of what it is that we hope to accomplish. And at these unstructured data meetups, what we really want to do is foster ideas, foster innovation, and collaboration around unstructured data, right? And you have this wealth of of activity and really awesome work that's being done around the models, and we want to do the same for unstructured data, for data that doesn't fit into a particular data schema or a data model, and so on and so forth. So that's really what we're looking to do with these series of meetups, and we're really, really glad to have you here with us, and we're really, really excited what sort of where things will go from here as well. So from this point forward, I want to give a quick primer on what are called vector embeddings. And vector embeddings are, we'll get a little bit more, we'll dive a little bit more deeper into this in the upcoming slides, but they're really important for us as we try to understand unstructured data. And these embeddings are, if you really think about it, they are words, or they are, sentences that are formed by machines, something that they can understand, a language that they can communicate in. So on the left, right, you see this image of of this. Well, it looks like I'm not quite sure what this is actually, but we see this image of a flower. It's got some. It looks like it's got some electricity moving through it. We understand this image from a human perspective, right? We can see these pixels and we can see this visual data and know exactly what it is and some of the things that it can represent, and maybe some of the things that sparks inside of us as well. So for example, a sense of curiosity or a sense of wonder, right? But computers don't really understand images at the pixel level. If you give it, an array of pixels, great, right? It's a representation of the image. I can draw it on a screen, but it doesn't actually mean anything to the computer. The semantic contents of that image aren't really there. And that's where embeddings come in. So by leveraging modern machine learning, right, what we can do is we can take images like that on the left and turn it into a representation that computers can understand on the right. So what we typically do is we take something like a knowledge base. It can be documents, it can be images, video, audio, or text, run them through embedding models, turn them into vectors, and store those vectors into a vector database. And I want to give everybody, again, another overview from 10,000 feet as to what each of these different components are doing, right? Your vectors in this case are semantically rich, meaningful words or sentences or phrases to a computer, right? We don't really understand them, but a computer does. And when you store them inside of a vector database, it's like storing them inside of, inside of the hippocampus. What is the analogy analogous to a hippocampus in a human brain? We store them inside of a long-term store, some sort of long-term storage. So this is really this particular framework here, the idea that we can take unstructured data, run them through embedding models, and store the output of those embedding models inside a vector database. This unlocks a variety of different applications across unstructured data. Things like retrieval augmented generation. So I imagine there are folks here who are familiar with how we can take context and expand a large language model's knowledge by incorporating different data sources, let's say from documents, from images, and from videos, and so on and so forth. You can build recommender systems out of them. You can match, let's say, products with users, or you can do user-generated content as well, and really give folks increase engagement and boost revenues and so on and so forth. Then you can do a variety of different types of similarity and semantic search. There's things like anomaly detection, AI-powered drug discovery. A lot of it is based on vector search and based on vector databases as well. And last but not least, we have things like multimodal similarity search too, which we will demo at the end of this presentation as well. So hopefully that's something everybody here looks forward to as well. So again, the idea of vector embeddings is that it is a representation that computers can understand, and with these, we can power a variety of different use cases. Before we dive into some of embeddings, I want to talk about the history of these vectors first, right? And I think there's going to be, hopefully this will be, to some folks, I think, this might be sort of old knowledge, or it could be maybe not too relevant today, but hopefully it's fun that hopefully we. The first thing that I want to start off with is talking about how these embedding models that we looked at, these embedding models that we talked about, if you really think about it, they are the true workhorses of AI-based applications, of generative AI applications, and a variety of other ones as well. And if we look at just a comparison, right, these are old numbers, right? But the model on the right is a large language model, and it's a Llama 2. So I know Llama 3 is out right now, but this is when Llama 2 was sort of at its peak in terms of popularity. And Llama 2 at that point had something like 770,000 downloads on a Hugging Face. And this is the smallest, most accessible version of Llama 2. And the model on the left is an embedding model. It is a pure text embedding model. And you can see across the same time period that this particular embedding model had over 5 million downloads. Now, there's many reasons for this as well, right? So, you have there's a lot of folks who, when they want to use a large language model, they just use an API. Perhaps it's not accessible. But if you normalize it by the sheer amount of embedding models that are out there compared to open source large language models, this is still a really, really impressive number. And I think it goes to show that there's a very, very underrated and value part of these AI applications, and that is, how do we generate these embeddings, right? That is these embedding models that we were talking about on the previous slide. Back in the day, if we wanted to generate embeddings for an image, or if we want to generate embeddings across text, we had to use these handcrafted features. So some of you might be familiar with this on the right. These are actually SIFT descriptors. And these are basically ways of, you take the image at different scales, You take, local extrema, and then you create a descriptor based off of that, and that is how you represent your image. You represent it as a bag of vectors or bag of words, right? So some of you may be familiar with this. And you would do the same thing with text. So that equation that you see there is actually the equation for TF-IDF, short for term frequency inverse document frequency. So that is the term on the left and on the right specifically. And that is a way, I'm not going to go into the details of it, but it is a way that you represent a document or long form text as a sparse vector. You could think of it that way, right? So we had these, we were way back in the day as well. We were already using vectors and we were already doing vector search, just not at the scale that we're doing it. In the lower right-hand corner, these are actually, this is the Harris corner detector. And again, another old way of detecting features inside of visual data. Today, though, if we look at these modern day embeddings, they are much, much more semantically rich and they're much, much more semantically dense. One of the key differences is that now when we have unstructured data, a single piece of data is mapped to a single embedding. So instead of, in this picture on the left here, where we had these feature descriptors, where the one image could have many, could have tens or hundreds of SIFT descriptors associated with it. In the case of modern day embeddings, we really have just one embedding associated with each image for most cases, right? Same thing goes for long form text. You have a paragraph, or you have a sentence, and you have a single embedding that is associated with that sentence. And this picture that I've showed here is a visualization of what these embeddings look like in three-dimensional space. Now, typically, these embeddings are something like 512 or 708 or 1024 dimensions, so they're much, much larger, they're longer. But this is after projecting them with UMAP down to 3 dimensions, so we can actually visualize them. And you can see they tend to form these sort of clusters and these interesting shapes as well. So embedding spaces are really, if you take actual image data, or if you take actual text data and you embed them, usually not spherical. There's a lot of interesting applications that you can not applications, but there are a lot of interesting side effects, I want to say, based off of this particular phenomena. But again, that's something that we won't get into in these particular set of slides, but I'm happy to chat with folks about it offline as well. So now that we have a primer on those embedding models and we understand why embedding models are good for vector databases and why you need them for unstructured data search, I want to walk through some modern day embeddings, right? So I want to walk through, how do we generate these embedding models today? And we're going to start with text. So recurrent networks, okay, I take back what I said. They're actually not how text embeddings are generated today, but they are good for understanding different models and how we actually go about to how these embeddings are actually computed from them. So in recurrent networks, you have this input state, X, you have this hidden state Y, and you have these, you have this hidden state A, and you have these inputs and outputs X and Y. And what you're trying to do is you essentially have a model that continually updates your hidden state. It takes a new input, and then it spits an output out as well. And that hidden state, if you really think about it, if you read in or if you absorb all of, let's say, the text or the image tokens that you have, the hidden state is a good representation of what that input is, of what your unstructured data is. That's really how recurrent networks work, and they really form the backbone, the precursor to what transformers are today. So again, if it doesn't make a whole lot of sense to some folks here, happy to chat about this a little bit more later on as well. But that's the idea, right? You have convolutional networks as well, and these convnets, again, they use a combination of convolutions and other layer types as well. So normalization, there's some residual layers in there as well. Sometimes you have pooling in there, average pooling or max pooling. And basically you take they have the idea of spatial locality. So you take, usually an input image, but again, you can apply convolutional networks to text as well. I won't dive too deep into that here in this talk. You can take convolutional networks, run it through a machine learning model, usually it's the penultimate layer of that model that you would take to be the embedding of your image data. Today, though, I think you see a lot more interest around transformers, and specifically around the idea of self-attention. And self-attention is essentially saying, hey, I have all these tokens. So whereas before in a recurrent neural network, I have all these tokens X at the bottom here, and I'm continually updating the internal hidden state of my recurrent network to generate better output states. In a transformer, what you do is you essentially have attention, not just to you don't have to store the entire state inside of this model, or inside of this vector that we call A. Instead, you can have every token attend to every other token inside of any sequence that you talk about here. At the end, what you typically do is you would say, hey, these output embeddings, and each embedding is a representation of one token. So again, this is for text, right? You can apply the same for images, but we'll get to that in a separate slide here. And the downside is that you have one embedding per token, right? It's very, very inefficient when it comes to retrieval and when it comes to using it in a vector database. So that's why we have things like BERT. When we do BERT, with BERT, we will do, we'll do pre-training, and usually that is with some sort of mass language modeling, loss. And once we have this pre-trained BERT model, what we can do is we can then say we're going to pool the output tokens of each of those, and we're going to do cosine similarity across them. We're going to fine tune the result of that BERT model, and then that is going to be a way that we actually embed, we turn long form text into vectors, and then we're going to have really, really good results based off of that. So that is that is the basis behind SBERT, or sentence BERT. So if any of you have actually used this sentence transformers library, that is actually most of the models that are on sentence transformers. This is the technology that underpins it. We take a pre-trained model, a pre-trained mass language model, a pre-trained model trained with MLM. We pool those features, and then we do cosine similarity across those features. We do some fine tuning, and have that be our embeddings for long form text. So for sentences, as well as for paragraphs, for documents as well. So the last thing that I want to talk about in this section is vision transformers, right? And there's the idea that we can take a single model, or a single model architecture, and we can embed not just text but images as well. That is a very, very powerful thing, not just for vector databases, for vector search, but for a variety of other applications as well. And when it comes to vision transformers, you really have the same thing. So what you're trying to do is now you're just tokenizing these input images. You patchify it. So generally they're 8x8 or 16x16 patches. You run those patches through what is usually a convolutional encoder, and you take the result of those patches, fit it into a transformer encoder, and run self-attention over all those patches. And then there's a single class learnable embedding, and that embedding is usually the output, right? So that embedding is not associated with any of the patches. Nowadays, instead of this particular architecture, what you see is the same thing as with sentence transformers as well. So you will do average pooling across all of the tokens that are in the image itself, and then you can fine tune the model to whatever you like across it, and that actually ends up being a really, really good representation of your input image. So a little bit different today, but this really forms the basis of what we're looking at for a lot of these vision encoders and vision embedding models today. So again, if we talk about how we generate these embeddings in really a lot of today's applications, the text embeddings that we talk about are usually some flavor of sentence transformers or some flavor of sentence BERT. So they're usually trained in two different steps. So they have some sort of self-supervised pre-training. So they have next token prediction, where they just do some masking. They predict tokens in the middle based on left and right context as well. And then there's usually some sort of contrastive or triplet loss, sort of fine-tuning based off of that. So you'll pre-train a really large model on a really large corpus of text, and then you'll fine-tune it on, let's say, on text pairs or text triplets. So there's if you see, there's a lot of embedding models that you see on Hugging Face, but many of those are just some flavor of this, right? So they will have, let's say, they might have sparse attention, or they might do different type. Might have different masking strategies, or slightly different objective function. But at the end of the day, the model architecture is very much the same. Today, for image embeddings, you will see, or for visual embeddings more specifically, so that includes images, video, and to a lesser extent audio, you'll see you'll typically see hybrid architectures is working the best. So they will have a combination of convolutions and self-attention. They're typically trained across this large, strong labeled or weakly labeled data set. The pre-training for images doesn't work as well as it does for text. It does work to a certain extent, but usually you'll see them trained across some sort of labeled data set. And then there's also, it's usually trained with categorical cross entropy or binary cross entropy loss. And again, that is a result of it being trained across these labeled data sets. That's a good overview of the embedding models that we're looking at, and how we generate them today, and sort of what some of the different things that we're looking at are when we are actually doing inference across these models for these vector databases. So one of the last things I want to talk about is multimodal RAG, and it seems like I actually have quite a bit of time here. I think I have an hour that was allotted to this particular presentation, so we can sort of do a second half, be a little more hands-on if any of you want to see something a little bit different as well. But here I want to talk very, very briefly about RAG, about retrieval augmented generation, and where things are going from there. So traditionally, RAG has been done, I'm actually going to skip this slide for now. Traditionally, RAG has been done across text. And for those who aren't yet super familiar with what RAG is, essentially what you're doing is you're taking a corpus of documents, running them through an embedding model, storing them inside of a vector database, such as Milvus, and using that vector database as a knowledge store, as a retrieval mechanism to get context into your large language model, to get context into your generative AI model. Right. So what you typically do is with RAG, when you have a search, you have a prompt, you would first run that prompt through your vector database, retrieve the most relevant documents associated with that prompt, and then add that context along with the original prompt and feed that to your large language model. This will give you more reliable answers. So, for example, if you ask a question that you need relevant context about, you can get better responses based off of that. And now with RAG 2.0, right, what you see is we're going beyond. We're going with a model that can take many, many different types of modalities, embed them all into the same space, and we do the exact same thing, except this time what we're doing is we're going to search across many, many different modalities of data for the right kind of information. So for example, a search is going to come in. We're going to do the same exact thing, except this time what we're going to do is we're going to find images that are relevant to our question, or images that are relevant to our prompt. We're also going to find audio snippets that are relevant to our prompt as well. And definitely, like in RAG 1.0, we're going to find documents and other pieces of text that are relevant to the prompt too. And based off of that, this is really where the whole concept and the idea of unstructured data comes in. We have all this, this wealth of data, and we have a model that can embed all of it into the same exact space, store it all in Milvus, and then we use the same form of retrieval to give us more reliable answers. I want to come back to this slide, and this is an embedding model called ImageBind. I'm not sure if any folks here have heard of it already, but essentially what it's doing is it's embedding 6 different modalities of data into the same space. So it embeds audio, images, video, depth images, text, and IMU data, so inertial measurement unit data, into the same space. And you can see this in action as you do things like cross-modal retrieval. So if I take audio, right, a crackle of a fire, I turn that into an embedding. I take images and videos of campfires or bonfires, and I do the same thing. I also take depth images of the same thing as well, and text that also describes that. these are all vectors that are really, really close to each other inside of this high dimensional embedding space. And by storing and searching across all of them inside of Milvus, I can get results like these, based on just simply by using this model. Same thing goes for, let's say, a baby cooing, right? If I have audio of that, I can retrieve images and visual data of, that is associated with a baby cooing. I can do the same thing for depth images. Typically what happens there is that it will retrieve, let's say, pictures of nurseries or cribs, and the same thing for text as well, right? So this is what, models like these, the models that can really embed many, many different modalities into the same embedding space. These are going to be the key sort of, I guess, workhorses of these AI applications moving forward. So as we see, models like OpenAI's GPT-4o, Claude, all these models, as they're starting to support images and audio natively, we're going to need ways of being able to do multimodal RAG across these different modalities as well. The last thing I'm going to mention, and this is because I still have quite a bit of time, is the idea that you can do embedding space arithmetic. This is something that vector databases haven't explored a whole lot just yet, but I think in the upcoming years, as vector databases become more of an unstructured data platform, this is something that could be very, very interesting. So what are we looking at, right? You have, if you take pictures of if you take pictures and you can add, so let's say, semantic relationships to them, and you can have these output results that are really, from a human perspective, very, very reasonable, right? So if I take this picture in the lower left-hand corner right here, picture of a heron, or of a pelican or something like that, and I add audio that corresponds to waves to this picture, I can get pretty much the same animal or the same family of animals, except now the backdrop is an ocean or a lake, right, or a beach. I can do the same thing with other modalities as well. So you can add, let's say, images with other images with text, and you can have these sort of semantic relationships across all of these different types of modalities of data. That's a really powerful thing that we're going to see moving forward. And last but not least, you have audio to image generation too. So you can, take an audio embedding, feed that into an image generation model, and you can get something that, is relative, somewhat resembles what you think it should resemble, right? So a dog, and an embedding for a dog, you feed that to an image generation model, you get what more or less looks like a dog. Same thing for engine fire and rain. So again, this is sort of multimodal data. This is I think going to be a really, really interesting area of research moving forward, is how do we build these really, really powerful multimodal models, and potentially how beyond these 5 or 6 modalities, right? How do we go beyond depth images, text, audio, and visual data? Maybe how do we add molecular structures in there, right? Or how do we add transactions in there, or how do we add other forms of unstructured data? I think there's going to be a lot of interesting work around this area moving forward. For these slides here, I actually do have a quick demo that I want to show folks. It's pretty short. It shouldn't take up a whole lot of time, maybe 5 minutes max. And after that, I'd be happy to answer any questions that folks have as well. So we have a good we'll have a good 15 or 20 minutes for that. And can you guys see the screen okay? All right, cool. So you can really think of this as a multimodal RAG demo. And I'm going to walk you through each of these, basically each of these cells and what's going on in these cells, right? And it might take me a little bit of time, but if you have any questions, if anybody has any questions, feel free to interrupt me at any moment, and I'll be happy to answer those. So what we want to do is we have, if I go back to this, right here, Nailed Bag, what I'm doing is I'm taking just text documents, feeding them to an embedding model, and storing them into Milvus. With RAG 2.0, what I'm doing is I want to have multimodal data stored inside of Mills. So what I've done here is this is the Google I/O pre-show. This is going to be my base for multimodal data. So if oops, so I'm not just going to play that here, but the pre-show is essentially this. There's there's a musician here, and he's doing this sort of forget what you call it. It's sort of like making music out of different things, basically, right? And there's a lot of interesting stuff that goes on inside of this pre-show, right? So this happened just a little bit late, a little bit earlier this year. And what I want to do is I want to store, index, and search this video inside of Milvus. So what I'm going to do here is, I've already downloaded this video here on my local laptop, but I'll share this notebook with folks after the talk, and you can always run this on your own as well. We're going to download this video. This is the video that we're going to be doing multimodal RAG across. We're also going to use Meta's new Chameleon model. So Chameleon, for folks who aren't aware, is an open source. It has 7 billion and 34 billion flavors. It is an open source model that allows you to, that gives you text and image capabilities together in a single large language model. And then we are also going to use this library called Radiant. Radiant is meant to, you can think of it as sort of like an ETL tool for unstructured data. So what we're going to do is we're going to first get this whole video into our vector database, right? And I'm actually going to run this first. This is just some imports that we need. And this cell here, what it's doing is I'm getting a path to where I've stored the video first. I'm going to create sort of 4 different tasks, 4 different operators using this video. So the first thing that I'm going to do is I'm going to read the video from my local drive. Right? I'm going to read the video from, let's say, a directory, or from, in this case, the path itself. I'm going to transform it using a video demultiplexer. And what this is doing is it's reading the video in and outputting audio snippets and images, right? So it'll take frames every 5 seconds, and it'll take it'll also have audio at every 5 seconds as well. And it is demuxing the video into these 2 individual streams of data. From that point forward, I'm going to vectorize it using this model that I talked about here, using ImageBind. ImageBind is, it's from Meta AI, and it is open. It's freely available to download and to use. And I'm going to vectorize both audio and images into the same space with this particular with ImageBind. And then from there, once I have all the vectors, I'll send them over to Milvus using the insert operation. I'm going to store all of them, right? If I combine all of these into a workflow, you'll actually see that you get all the data stored in there. Now, I've already run this on my local machine. So if you actually download the video here, it is fairly long. It does take a while to do all the processing. So I'm not going to run this cell here, but I will run this cell down here. And what we're really looking at is, once I've inserted all my data, once I've run all of these individual operations inside of the workflow, I can do the same thing searching across that data too. So what I can do is, now I'm doing the same type of vectorization, right? I am using the ImageBind model, but instead of having a multimodal model, right? So something that can accept any type of modality. Now I just want to vectorize text. And once I vectorize that text, I want to search what I've stored in Milvus, right? I want to search, I want to do that search, and I want the results based off of that. So what I can do here, I'm actually going to run this. I'm going to run all of these actually. And as these are run, you'll sort of see that we can sort of see each of these individual steps that are occurring as well. The prompt, when in this next cell down here, what I'm doing is I'm taking a prompt. So in this case, I'm asking what was unusual about the coffee mug. And if I go back to the Google I/O pre-show, you see that in the intro, there's this coffee mug, and the musician actually climbs out of it. So he sort of climbs out of this coffee mug, And then he starts playing across all this. Mark climbs on this coffee mug before he starts doing his set. So if I go back to this demo, now with this prompt, I can actually retrieve the most relevant information that is associated with this with this data. So I can actually just run this. I'll sort of walk through what's going on here as well. I'm giving Milvus some search variables, so I'm limiting it to the top of one result. I want output fields that give me the relevant information that I can then feed into my large language model. And then I have a filter that I can use as well. So this filter, what I'm doing is I'm filtering out content.
The recording has
audio.
stopped. This meeting is being recorded.
Content that is not audio, so that it doesn't have, because Chameleon for the time being only supports text and image modalities. So if I run this, right, and then I look at the results, you'll see that actually gives me this result right here, right? And I'm actually going to, let me see if I can pull an image of this quick. Give me 1 sec. In 1 moment here, folks. Just do it down here. So that's what this image looks like. So with multimodal retrieval, right? Again, what I've done is now my prompt here is what was unusual about the coffee mug? And what this model and the combination of ImageBind and Milvus have given me is the ability to search for images and audio streams based off of some text, right? And that is really, really powerful. I can do this same thing here. I can modify it. So if I want just audio as well, I can do the same thing. Less relevant than the image, but it's still somewhat relevant as well. I unfortunately can't play audio here on the stream, but I definitely encourage folks to go and try it out themselves after this talk here. So again, I can also increase the number of results that I search for. So in this case, whoops, what's going on here? So in this case, I can see 0, 1, and 2. So these are all images of the coffee mug itself. So for example, I can take these. This is another result and another result based off of that, right? So you can see clearly that there's some unusual stuff going on with this coffee mug. And this is what we can then feed into the large language model to do, let's say, analysis or to do reasoning over. Now, once we have all of that data, what we can do is we can then just pass it into our large language model. And I'm not going to do, I unfortunately can't run this cell here on my local laptop. I just don't have enough GPU memory to be able to do it. But this is the code that you would run to do inference over Meta's Chameleon. And again, as long as you make sure you download the model weights and you install Chameleon locally, you can actually run this cell. So what I'm doing here is I'm passing at the end the text, and then this is one of the outputs that's given me. So, it says that the unusual aspect of this coffee mug is designs resemble the logo of a well-known tech company, Apple, which is not entirely, it's not 100% there. Again, because this is a pretty small model, it is Chameleon 7B. If you use something a little bit larger, or if you wait for Meta to train their largest model, it might be a little bit better. But yeah, this is a really, really quick demo of multimodal RAG. Very, very easy to build out. It's really just taking traditional RAG and at the embedding layer, at the model layer, doing things and running a particular model that will actually allow you to embed multiple modalities of data into the same exact space. Any questions? All right. I'll figure out a way to share this with all the attendees after this talk here. But what I want to do is I also do want to go back here. We do have this QR code here as well. And again, this is the demo that we just did is based off Milvus. Specifically, it's based off of Milvus Lite. So there's a light version of Milvus that runs directly inside of any Python-based environment. So if you scan this QR code, you can go there. You can go ahead and check out that repository as well. So I think for from this point forward, I'd love to open up the floor to questions. I do want to say thank you to the organizers for having me come on and talk about not just vector databases, not just unstructured data search, but about embedding models and about computer vision and natural language processing as well.
Thank you, Frank. This was a great talk. Thank you so much. And we are going to open to questions if anyone has questions. Yeah.
Hi, Frank. Thank you. Wonderful presentation. It's very intriguing, this space with multimodal language models and what you can do. I'm a technologist, yeah. I write technical articles and have newsletters. And I just thought about, how you could use this multimodal vector search, and for example, in cybersecurity. Yeah. So if you could have embeddings, vector embeddings to try to narrow into what could be a sign of a breach or a compromise from your cameras, security cameras, together with unusual activity in your servers or user actions. Have you heard about it, or have you seen use cases in that from that perspective?
Yeah, absolutely. I'm actually going to take this in two different directions, and one is just security more broadly in general, and the other one is cybersecurity and fraud detection, really. So for security in general, if you use images and generally these will use images and other forms of visual data, such as videos. And by vectorizing either the actions in these images or what's going on in these videos, or sort of frames side by side, what you can do is you can detect, let's say, someone climbing over a fence, or you can detect someone let's say running a red light, right? These are things that you can do with vectors specifically. We've actually seen a lot of them built out. I've personally seen a lot of them built out by some of our users, not just but of Zilliz Cloud, the Zilliz Cloud platform as well. So that's one route, right? That is sort of more the physical security route. When it comes to cybersecurity, vector databases are also very, very applicable. So I'll give an example of fraud detection. So if you're a big bank, for example, and you have all these transactions, and these transactions, what you want to do is you want to find, let's say, ones that are similar to transactions that have happened before. You can take all of these transactions, embed them, store your previous transactions into a vector database, and by searching for the most relevant or the most similar transactions to one that has just happened, you can determine whether or not it's fraudulent. That's actually a very easy and extensible, flexible way of doing fraud detection for a lot of these, for the financial industry or for the legal industry. And the reason is because oftentimes you'll want to relabel, right? Oftentimes you'll want to correct something that happened before, something that was mislabeled as fraud, or something that was fraudulent but did not go labeled that way. If you can go and correct that very easily inside a vector database with that original vector associated with it. Same thing for, let's say, detecting viruses or detecting threats. So one of the things that you can do is you have applications where you have APKs, executables, and you vectorize the contents of those. You might not vectorize it with, let's say, a machine learning model, but what you could vectorize it with is with some handcrafted features. So for example, you could look at the number of times a particular APK does a network call, or the number of sockets that it opens, or how many thread it runs, and how long each of those threads run. Each of these different features are inputs into, let's say, or they can be that you can vectorize. each of these features combined together can be turned into a vector, and you can search for nearest neighbors vectors inside your vector database to determine whether or not, hey, a particular application might be fraudulent. So there's many, many different ways that we can use vector search. And again, because vectors, I'm gonna go to this slide here. Because vectors are something computers can understand really, really well, that's why it's extensible to so many different applications, not just the ones that you see here, but beyond here as well, like AI-powered drug discovery, fraud detection, antivirus, so on and so forth. So great question, Gabrielle, and I hope that answers it well.
Thank you. Anybody?
Hi, Frank. Thank you for your presentation. I'd like to know, aside the visual and test data, are there another kind of unstructured data that I can search and store by the using of data vector database?
Yeah, great question. And I'm going to leverage this diagram here too. So any type of data that you can run a machine learning model through, or that you can generate vectors of, can be stored inside of a vector database. So some examples are here on this slide. So for example, you have audio, images, video, depth images, so 1D images, text and IMU data as well. That's not represented in this particular slide, but IMU data, all these different types of data can be stored inside of a vector database. But I'm going to give you less boring examples too. So for example, you could store 3D structures. You can store geospatial data. You can even store time series data inside of a vector database. You can take graphs and you can vectorize them and store the nodes, representations of each node in the graph inside of a vector database. You can molecular structures. Again, for AI-powered drug discovery, it's one of the common ways. That's vector search is one of the common ways, or one of the ways that's used to discover new drugs. So you can vectorize molecules and store those molecules and store the vectors associated with those molecules inside of a vector database. You can store bank transactions or financial transactions. You can store a combination of any of these different types of data. So oftentimes, if you have a PDF, you have some sort of document, it combines all of these modalities together, and you can average all of them and store all of them inside of a vector database too. So really, any type of data that you can vectorize, that you can get a feature descriptor over, right, can be stored inside of a vector database. And really, I think the applications and the number of modalities of data that you can use really are limitless here. Anything else I can help answer? Happy to take questions.
Okay.
Oh, you're very welcome. Yeah.
One more. Thank you, Frank, for the presentation.
Sure.
We know you are aware that there is no tool that fits all the problems. So you showed to us some different embeddings. And at the company level, how do you deal with the selection of the embedding that you are using? Because I'm asking that because the technology is running very fast. So I believe that you have a problem at your side. So how do you select the most appropriate embedding depending on the data?
Yeah, that is a great question. I will give you an example, actually, a recent example that I encountered. And there's this company that we're working with. They're building conversational AI. And it's pure text only, right? Just a single modality of data. And they said that, hey, our results aren't that great. Our results are not as great as the competitors. And one of the things that we're looking to in terms of advice from you is, how do we make our results better? And again, they were using a vector database. They're using Novus. They're using Zilliz, and they want to figure out a way to make their conversation, to make that retrieval step a little bit better. And the first thing that we did was actually sit down and take a look at their embedding model. and we analyzed what their embedding model, the data that their embedding model was trained on, and maybe some of the potential shortcomings. And we sort of sat down and did a bit of an analysis over what the desired results were versus what the actual results were from the embedding model. And we discovered that this particular embedding model we're using was simply not trained across their modality data. It was not trained for conversational retrieval, not trained for conversational AI. That is the key thing to remember, and that is the key thing to watch out for when you're working not just with vector databases, but with embeddings in general, is that you have to understand the underlying model. You have to understand the data the model was trained on, and also how it was trained too. That's also very important. The key thing is data is by far the most important. So if you have, for example, if you have legal documents, right? And you're picking an embedding model to work with those legal documents. You want to vectorize them and store them inside of Zilliz Cloud or inside of Milvus. You'll want to make sure that you have an embedding model that was tuned to that particular task. And there's many layers here, right? So for example, I can go to Hugging Face. And if I search for models that are, let's say, people, I can search for example, here is a legal BERT base sort of a model, right? I have to understand the data that it was trained on, right? Is it trained on, let's say, legal analyses, or is it trained on rulings, or is it what is it trained on specifically, and whether that really matches what my application is looking for. Don't just pick a random embedding model. Actually, the key thing that I tell most of our users is not to use OpenAI embeddings. And the reason is because there's no one-size-fits-all embedding model, right? You have to have embedding. If you want to extract the maximum performance out of your vector database, you have to experiment with different embedding models, find embedding models that are relevant to your data, and then maybe try different retrieval techniques as well. And then that is the key thing to remember. I wish I could give you a more direct answer, but I think there's opportunity there too, which means that this is more of an engineering challenge rather than something that is just purely about machine learning. I hope that helps.
Thank you.
You're very welcome. Yeah.
Okay. So there are so many tools, there are libraries that you can work with. How would you summarize, the benefit of working with the purpose-built, vector database, and what is offered as the pipelines to facilitate exactly that, what you said, finding the right thing, using the right thing at the
Yeah. Great question. I get this question a lot. People ask me, why should I just not use PG Vector? Why shouldn't I use Postgres's vector search capability? Or why should I not use MongoDB? Ask whatever, right? And at the end of the day, I like to say this. A lot of traditional databases, a lot of document databases, a lot of search engines are building vector search capabilities into their platform, or they've already built it. At the end of the day, the reason why you want to pick a purpose-built vector database is because you want to unlock the best performance, and you want it to be the most attuned with, you want it to be the most AI native. You want it to be most attuned to different AI applications. I'm not trying to bash, let's say, MongoDB, right? MongoDB has their Atlas vector search product, which is great. I've tried it, I've used it, it's good. But the thing about MongoDB is that the culture around it and the community around it is really document search, is searching JSON documents and object documents. And vector search is not their primary focus. It's not the primary thing that MongoDB does well. If you have a vector database, vectors are the primary thing that it does well, and things that are based around those vectors as well. So for example, in Milvus, we have things like range search. You can search a range of vectors around that. We have hybrid search, the ability to search across sparse vectors and dense vectors, right? Those unlock capabilities that are in structured data that you wouldn't be able to do with something like MongoDB's Atlas vector search. I want to take that one extra layer as well. And in Milvus specifically, it's not like Milvus or any of these other vector databases, it's not like they don't support structured data. They do. In Milvus, you can support metadata, right? In Milvus, I'm actually going to bring up the docs right now. In Milvus, you can build indexes over strings, over floating point values, over ints, and over and eventually you can store things like arrays. You can store JSON inside of Milvus as well, and you can query over it too. You in a vector database, in a purpose-built vector database, it can support JSON documents, right? It can support traditional text search. It can support relational data. It's not that vector databases don't support the other data types. It's just that we choose to focus on vectors. And while these other databases, they choose to focus on other aspects as well. So if you want something that is AI first, that is vector first, vector centric, you should always choose a purpose-built vector database. But if you have an application that, let's say, you don't need a whole lot of AI features that are based into it, that are built into it, I think that's when it makes sense to use something like Postgres. And only when you want to do some experimentation, you can use PG Vector, right? So that's my 2 cents. I know a lot of, if you talk to someone from DB or you talk to someone from who's working on Postgres, that probably will have a different than I do. But that is, I think, one of the ways of thinking about it is if you want your application or whatever you're building to be AI native, to be AI first, you should always use a purpose-built vector database. And it's simply because we as a community, as a Milvus community, we are more attuned to the needs of developers around AI and machine learning.
Thank you. If you have one more one more minute, I do have
Sure.
another question. As you were talking about, all these different
Sure,
kind of
sure.
data, and I see that there are large language model that's Muda model, and you also have the vector database that is Muda model as also. What is the difference between doing a search using the power of the vector database with Muda model kind of data, or just using a large language model that's Muda model? I don't know if there is any difference or if it is the same case with RAG.
Yeah. Multimodal RAG, really, the reason why you want RAG 2.0 or multimodal RAG is because you have multimodal language models now. So I know that sounds weird. I like to call them large multimodal models. So you have capabilities that you have models that can take text and images and combine the two modalities together seamlessly. So you could have an image of, let's say, you could have an image of of some bread, and you could tell the model to generate a recipe that can make what's in the image for you. Stuff like that, right? But basically what I'm saying is just ways of combining many of these different modalities. And if any of you have watched the GPT-4o video, or the GPT-4o, they did a little demo of that probably about a month or 2 months ago, you'll actually see that they support audio too. You can talk directly to the model. You can give it sound effects. You can give it music, and you can have that model respond for you in ways that, quite frankly, are pretty amazing. That is why we need RAG 2.0. That's why we need multimodal RAG, is because the large language models are becoming large multimodal models, right? It's because they're no longer LLMs, but now LMMs. We need to find a way to do retrieval over these different types of data, over text, visual data, and audio data, and feed that data into a vector database. And moving forward, you're going to have these models that you're going to have large models that are capable of many more modalities as well. So, for example, they're capable of reading in-depth images, just as they are capable of processing text and images and audio. And the same will go for other data types too.
Thank you.
You're welcome.
Any more questions? It's okay. Frank, thank you very much for the presentation. I think everyone liked it a lot. And I
You're
don't know if you have any final comment on final speech.
Yeah, if you would like to get in touch with me, feel free to add me on LinkedIn, give me a message on Twitter. And if you want to take a look at Milvus itself, here's the link to the website, and here's the GitHub as well. The GitHub is milvus.io/Milvus, and the website's just milvus.io. And we definitely welcome, any and all comments. We want to be in the unstructured data space more broadly, and we're always happy to have more folks that are contributing as well. So thank you again for having me on and having me present here, and looking forward to more of these in the future too.
Thank you. We'll have a close. I have to close your microphones just for a while.
All right.